In this video, we're going to be looking at waves in the universe. Okay, so this is sort of like the third topic that you need to get your head around in terms of the unit P1 of Edexcel physics. So let's get straight into that. So as usual, I'll go through the grades first, and I'll go through the rest of the work that we need to go through after that. So first thing, you need to define the following terms: the solar system, the Milky Way, the galaxy, and the universe. Okay, so the solar system, that is just the sun and all of the planets that go around it. That's pretty straightforward. We've got the Milky Way, that is our galaxy. Okay, so that contains our solar system, other stars, potentially other solar systems as well, but just not ones that go around our sun, ones that go around other stars. Okay, galaxy is a collection of billions of stars, and the universe is a collection of millions of galaxies. It's the following order of size: so the universe, the sun, the earth, the moon, and the solar system. So the smallest of those is the moon, and then the earth, and then the sun, and then the solar system, and the largest would be the universe. Okay, so that's pretty straightforward. Now I want to describe the life cycle of a small sun-sized star. At the same time, I'm going to describe the life cycle of a larger star. Okay, so I'm going to do these two first, so grade B and grade D, and I'll come back to grade C afterwards. Okay, so to describe the life cycle of a sun-sized star, let's skip down to the part of the document where I've got a lovely diagram of this over here. The life cycle of a star. Okay, so stars are essentially made of dust and gas. When that dust and gas comes together, the dust and gas is known as a nebula. When that comes together, it's pulled together by gravity. So gravity is pulling everything in. That kickstarts a process called fusion, and that pushes out. So fusion pushes out, and gravity pushes in. So let me draw a little something over here. Okay, so I'm not going to be able to draw there because I'll come off the page. Okay, so if I draw a little diagram here, gravity is going to be pushing everything in. It's going to want to push everything closer and closer together because of gravity. As it's pushing all these atoms really, really close together, it's going to create more and more pressure, which will kickstart a process called fusion. Some F at the front. Fusion. Now fusion is going to create its own energy that's going to push out. So it's the fusion energy that pushes out. When those two are balanced, that's when the star stays at the same size. Okay? So any small masses that are left behind from this process, they go on to make other planets. When the star is in its main sequence, these gravitational forces that are pushing in are balanced by the radiation pressure or fusion pushing outwards. Okay, they're balanced, so the star is stable in its main sequence. So first is a nebula, then it ends up being main sequence. Okay, so first is a nebula, then it ends up being main sequence. Now, depending on the initial mass of the star, it either is going to go on down one route, like our sun, or follow a route of a much larger star. So our sun is a relatively small mass star. Let's follow the route of that. Okay, so that will swell up, it will become a red giant, then a white dwarf, then a black dwarf. So small stars go from a nebula to main sequence, to a red giant, to a white dwarf, to a black dwarf. If they're much larger, there's much more fusion that takes place due to much larger gravity. So after the main sequence, they end up getting red supergiant, not super red giant, but red supergiant, supernova. Then they either become a neutron star or a pulsar, and sometimes they go even further and become a black hole, and we call that a singularity as well. So that's grade B and grade D done. The thing that affects which route it goes is the mass. Small mass stars end up like our sun, a black dwarf. Large mass stars could end up being a black hole, but definitely go supernova. Right, grade C work is what we need to look at now. Now, if I remember correctly, this is looking at different types of telescopes. Scopes like that. Yep, okay, so discuss the advantages and disadvantages of placing a telescope in orbit when compared with an earthbound telescope. Okay, so we've got to think about what happens when you place telescopes in different areas. So in orbit, it's going to be able to get around the atmosphere and the issues caused by the atmosphere. However, in orbit, it's going to be a lot harder to actually maintain. So here we go. We've got some examples over here. Some telescopes are placed in space. The problem with earthbound telescopes is that the Earth's atmosphere gets in the way and stops us seeing objects in space. The atmosphere can absorb parts of the electromagnetic radiation, and therefore objects cannot be detected. So the problem is the atmosphere is getting in the way. It's stopping us from absorbing, say, ultraviolet and looking at stars in the ultraviolet part of the spectrum. Telescopes in space, though, are harder to maintain and they're more expensive due to their location. Okay, so the advantages of the space are that no electromagnetic spectrum, no part of the electromagnetic spectrum will be absorbed. The atmosphere will not get in the way. However, the disadvantages are they're expensive and they're harder to maintain. So therefore, the advantage of being on Earth are they're easy to maintain, okay, and easy to upgrade if required. The ones on Earth, but the disadvantage on Earth is that some wavelengths will be absorbed by the atmosphere. Okay, so that's grade C done. That takes us to grade A because we've already done grade B. It says compare and contrast the Big Bang and steady state theory. So we're going to look at the Big Bang theory and the steady state theory. Explain how CMB, or cosmic microwave background radiation, CMBR, was discovered and how it led to the Big Bang theory becoming the accepted model. So we've got to get our head around the steady state model and the Big Bang theory. Okay, so let's find that section. It's just over here. Okay, so we know that everything in the universe came about 13.5 or 13.7 billion years ago. Okay, well, we believe all the matter in the universe was in a very small point. That point then expanded out. Okay, and we call that expansion or that explosion the Big Bang. There have been other theories in the past as well, and the main one of those is steady state. Steady state, and here's what steady state actually is. It states that the universe has always been in existence and expanded as new matter has been created. Okay, so it states the universe has always been there, and so when new matter is made, it expands a little bit more. So steady state has said the universe has always been there. Big Bang said it started at a specific point in time. So they're the two main theories. Nowadays we believe in the Big Bang, and the reason why is twofold. The first one, the absolute smoking gun that cannot be explained using steady state theory, is cosmic background microwave radiation. This is a heat signature that's left over from the Big Bang. Okay, so just like when you fire a gun and smoke comes out of it, same idea here. It's a heat signature that's left over from the Big Bang. The Big Bang is the only model that can explain the existence of cosmic microwave background radiation. Okay, it's microwave radiation that is coming from every single direction in space. Okay, originally when people discovered it, they thought it was a fault, but then now they know that it wasn't a fault. That actually is microwave radiation coming from every single direction of the sky. Another piece of evidence that contributes towards an understanding of the Big Bang theory, although isn't a smoking gun for it, isn't direct evidence. Okay, this can be explained by steady state, not very well, but it still can be explained by steady state. Is the idea of the redshift. Okay, now I'm going to go for the redshift right now. I know it jumps onto a later grade, and so therefore I know it's coming up, which is why I'm going to talk about it now. The redshift shows that the universe is expanding. So it doesn't say there was a Big Bang, it shows that it's expanding. All of the galaxies are moving away from each other, okay, which means that the light is redshifted. The Big Bang model predicts that they're all moving away from each other. But the redshift can also be explained by the steady state theory. So that's what I was saying. This is not a smoking gun. Both theories can explain this, although the redshift does back up the Big Bang theory when the Big Bang theory says that all galaxies are moving away from each other. So what's actually happening? Well, stars give out some light, like so. So here's a galaxy with loads of stars in it and it's giving out some light like so. Imagine that galaxy is stationary, it's not moving. The wavelength from it was fairly consistent. If the galaxy is moving away, the wavelength gets stretched out. This is the same wavelength as this, however, it's different because this is moving. Okay, these galaxies are the same, they give out the same wavelength, but the observed wavelength is longer, and that's the key phrase, the observed wavelength is longer. Okay, the observed wavelength is longer, and the reason why the observed wavelength is longer is because the galaxy is moving, and as it moves away it expands out that wavelength. The actual wavelength hasn't changed. We say the observed wavelength has changed. The observed wavelength is longer. Okay, this means that the galaxy appears redder than it should be. It's not actually redder, it just appears redder, and therefore it's been redshifted. Why red? Because red is a longer wavelength than orange or blue. So if it was orange and it's got redder, it's moved towards a redder spectrum. Okay, that's a longer wavelength. So what if it's coming towards us? What if it's coming towards us? It's going to end up with a blue shift. Okay, oops, I'm just jumping past that bit. Okay, so if it's coming towards us, it'll end up having a blue shift. Okay. Now, the thing with the blue shift okay, is that it tells us that galaxies must be coming towards us. If galaxies are coming towards us, the wavelength is therefore getting shorter. Okay, the whole reason this occurs is because of something called the Doppler Effect. Here's the Doppler Effect here. That's what I was trying to show you. This is a key idea here. The whole of this section here on the Doppler Effect is very important to know. So Doppler Effect is caused by the relative motion of a source of waves compared to an observer. So if one of them is moving compared to the other, you get the Doppler Effect. So as a police car comes towards you, the frequency gets higher. In other words, the wavelength becomes shorter. As the car goes away from you, the frequency gets lower because the wavelength gets longer. That changes the pitch. Higher pitch, higher frequency. And vice versa. Lower pitch, lower frequency. Okay, it can also be investigated by moving a ball. So if that ball is spinning around, if it moves towards you, okay, then the wavelength will be getting shorter, therefore higher frequency, higher pitch. And if it comes away from you, wavelength will be getting longer, lower frequency, lower pitch. Okay, right. I think that's everything from that sheet. I'll just double check that, and then there's a couple of extra bits I need to go through. Yep, so it says explain how it started with Redshift and explain why the Redshift provides evidence for an expanding universe. Remember to include words such as wavelength and frequency, so we've done that. The only other thing that I need to include, okay, is this little bit here about different telescopes. Different telescopes, okay, can pick up different stars. Now you don't need to know that in a lot of detail there. Okay, but just know that we use different wavelengths because they allow us to see different things in the night sky. Okay, over here, a bit more. Searching for life, okay? We believe there could be alien life out there in the universe. Okay, we believe there could be alien life out there in the universe. So one of the things we've done there is we've sent out Pioneer 10 and 11, okay, to actually look into this. Okay, we've sent out plaques on probes, okay, like this plaque over here. Okay, like this plaque over here. We've sent out some plaques on probes to send information about where we are. So you can see that's telling us. Telling aliens, if they were to find it, where we actually are. We've analysed radio waves come from space, looking for patterns, looking for signals, and hopefully we might find something one day which tells us that we are not the only life in the solar system. We use more than just optical, because not all objects give out optical or visible light. Some give out infrared, some give out others. Okay, so telescopes such as the Hubble Space Telescope are there in outer space, so there's no atmosphere to actually get in the way of them. And that's what we were talking about before. Okay. And that's everything that you need to know about waves and the universe.